All right, so now let's talk about the remaining two functional groups, thiols and ethers. Remember, thiols, they're a lot like alcohol groups, but instead of OH, they contain SH. They tend to have really strong odors. Some of them on the pleasant side, like as in onions or garlic, cheese. Other times, very disgusting, such as like skunk spray. Okay, so they just tend to have very pungent odors. Yeah, so let's sort of look at some of these. These are, I guess, the more pleasant ones, such as methane thiol, which you can find in cheeses and garlic. So let's actually look at this name real quick. So first of all, one carbon. So that's where we get our similar meth prefix. And then instead of, right, so methanol, oops, let's actually do it here. This was CH3OH, that would be methanol. When it's a thiol, we actually put that whole word on the end, right? So now this has the thiol suffix. So an ol is an alcohol, a thiol is a thiol. And like I've sort of been prefacing before, because, you know, we don't say methanol, it sounds weird with those two consonants running together. So instead, we don't drop that consonant, we keep it, and this would be methane thiol. Okay, so that would be our simplest thiol, would be methane thiol. Likewise, up here, we can take a look. So this is the one of the sort of active ingredients in onions is 1-propane thiol. So let's see if we can pick this name apart. So we have a 1 and that thiol ending, and that's because we have our thiol group located on carbon 1, right? And then it's 3 carbons long, so that's what makes it propane thiol. Okay, and another compound that would be found in garlic would be 2-propene 1-thiol. Notice that that has a little bit trickier of a nomenclature scheme because it has both a double bond and the thiol group. So actually, you have to stick that 1 in the middle right in front of the thiol to indicate the position of that, where the 2 out front is telling you where the double bond is. I don't want you guys to get too hung up on that. We don't need to learn how to name every compound under the sun in this course. We're going to tend to stick to the simpler compounds within a particular functional group that we're discussing. It's good if you can like reason through why that name would be there. Whether or not I would expect you to come up with it from scratch, no. Okay, so let's do one of these together real quick, see if we can't get this nomenclature of thiols down. Again, we're going to number our parent chain, which in this case would be this right here, in such a way that gives that thiol group the lowest possible number. So we have 4 carbons, so we're going to use that but prefix, and located at carbon 2 is our thiol group. So this is 2-butane thiol. Again, I'm not dropping the E like I would if it was an alcohol, right? So I guess just for comparison, this would be 2-butanol. The analogous thiol, where I'm only really switching an oxygen for a sulfur, would be 2-butane thiol. Okay. Yeah, same deal. Okay, so now going to ethers. Ethers are one of the still commonly used and also historically anesthesias. Okay, so I don't know if you've ever seen one of those old movies and somebody has a rag and they hold it up to the person's nose and they fall unconscious. What they're sort of claiming to have there is diethyl ether. Is the common one that you would use to like knock somebody out if you were in the mafia or something. I don't know. But yeah, so ethers are something that when we inhale, they sort of just knock us out. They interfere with our system. An ether is an oxygen that's single bonded to two different carbons. Those carbon groups can be sort of any size. There's not really any restrictions on that, right? So for example, you could have a very simple ether where you just have it bound to two different carbons. Or you could have a more where one side's larger than the other. You could have an asymmetric ether. You could have a benzene ring on one side of your oxygen. Anytime you have an oxygen single bonded to two different carbons, that would fall in the ether category. Okay, how do we go about naming ethers? So basically what you do is you look on either side of the oxygen first, okay? We're going to learn both the common and the Iupac way of naming ethers. For whatever reason, I think because they are very commonly used as solvents, the common names for ethers have stuck around a little bit longer than some of the other ones. So going back into the stockroom and seeing something like diethyl ether, that might literally be the name, even though that's the common name, not the Iupac name. But that could very much so be something you would find written on the bottle. So we are going to learn the common names for the simpler ethers. They're not too bad though, trust me. So first thing we do is we're going to look on either side of the oxygen and figure out how many carbons we have, right? So this, on one half, I have just one carbon, so that's a methyl group. On the other half, I have 3 carbon chain, so that's a propyl group. So for my common name, I'm just going to take those two substituents and put them in alphabetical order. Methyl, propyl, ether. And there actually is a space in between these substituents. Usually we don't put spaces, but in the case of naming ethers, we do. So methyl propyl ether in this case. Okay. We can do another one, another simple example. So here again, I'm going to look on both sides of my oxygen. This is an ethyl group. This is also 2 carbons, so that's also an ethyl group. So this would be diethyl ether. Okay, those would be the common names. If I want to do the Iupac name, I actually sort of start doing the same thing. I'm going to look on either side of my carbon, or I'm sorry, either side of my oxygen. So here's my 1 carbon methyl or ethyl group. Oops. 1 carbon. And then on this side, I have this 3, holy cow. On this side, I have these 3 carbons. Okay. And then what you're going to do is whichever group is smaller, you're going to lump the oxygen in with that group. Okay. So this was the smaller in terms of the length of the carbon. All right, so we lump the oxygen in with the smaller half, whichever one has fewer carbons. The other half is going to become our parent chain. So this half here with 3 carbons will be our parent chain propane. Okay. The other half is our substituent. So notice that it's going to be located at position 1. So this is going to be 1. And then what we call this type of group is methoxy. So meth being because it has 1 carbon, and the oxy meaning that it has that oxygen from the ether. So this would be 1-methoxy propane. Okay. I just want to point out real quick, not all ethers have common names. They have to be relatively simple. So this particular one does have this methyl propyl ether as a common name, but if it was 2-methoxy propane, that wouldn't have a common name associated with it, right? Because I could have instead had I guess let me just draw it over here just because this is blank. I could have instead had CH3, CH, CH3O, CH3. This would be, again, I have my parent chain that's 1, 2, 3 carbons long, but this would be 2-methoxy propane. Okay, so we're only going to worry about common names for the simplest of ethers. All right, so let's go through this procedure one more time so we make sure we got it. First thing I do, I'm going to separate my molecule and look on either half of the oxygen. So over here, I'm going to put this in a chunk. And then over here, I'm going to put this in a chunk. Which one's longer? Because that one's going to be my parent chain. So in this case, it's the green one. This becomes my parent chain. And it has 1, 2, 3, 4 carbons. So my parent chain is a butane. And then that means I'm going to lump my oxygen in with this smaller group here. Over here, I have 1, 2 carbons. So this is going to be F-oxy. And so this would be 1-F-oxy-butane. If I wanted to do the common name, it would be a little bit easier. Again, I'm going to do the same thing where I'm going to cut and cut, but then I'm just going to name each group. So for example, this will be butyl, this will be ethyl, and then we're going to arrange them in alphabetical order. So this one would be butyl, ethyl, ether. Again, this would be common name, and this one would be the Iupac name. Again, just to sort of comment a little bit more about ethers and their use as antiseptics, or I'm sorry, anesthesias. So what does an anesthesia do is it causes you to lose not only consciousness, but also sensations such as feeling and importantly, memory loss as well, right? Because you don't want to wake up and remember that you were just in a crap ton of pain during surgery. So it really blocks all of those sort of receptors, but in a reversible way. When you wake up, you don't have any lasting side effects like brain damage, right? So it's kind of amazing that they're able to do that. Again, simple ethers were used for a really long time. The problem is that they're incredibly volatile and incredibly flammable. So a doctor's office or an anesthesiologist's office was a very dangerous place 50 years ago when we were using things like diethyl ether because of just how incredibly volatile, meaning the room can fill with the gas, with the vapors, and then flammable, meaning of course then those vapors can combust. Okay, so could be quite dangerous. The way that they sort of have got around it, so these are sort of an illustration of some of the more modern ones, is they replace a lot of those hydrogens with different halogen groups, so fluorine or chlorine. That has a tendency to both decrease the volatility, so it's the ability, the ease with which they go to the gas phase, as well as the flammability. So that's why they're a lot safer nowadays.